So this is decision version E. Starting off with section A, building a rockery. Now this has got to basically be a critical path analysis one. So where we've got something like this, it means we don't have anything happening beforehand. So if we start off, we've got A at the beginning, and A has a duration of 2. B, again, doesn't have anything before it. B also has a duration of 2. C has to wait for B, so this will come out of B.
But 6 times. So you hold it for 10 seconds, you rest it for 30 seconds, and then do it all again.
And that has a duration of 4. D, again, has nothing happening first. So we can put D in, and that has a duration of 3. So E has to wait for C and D. So E is going to come out of C and D. So that's E. And E has a duration of 2. F only comes out of D. And F has a duration of 1. G has to come out of E and F. So G has a duration of 1. H comes out of G. And H has a duration of 3. I comes out from F.
I think it's not what I've done historically, but I'm treating it very much scientifically. So I'm following the process.
So I has a duration of 1. And then lastly we've got J. And J has to wait for A, right back here, G and I. So we've got I, G and A, and all of those are going into J.
So this is the top layer.
So we're in a situation where we don't have a single endpoint, so we have to make sure that we have an end. And everything that doesn't go somewhere else is going to have to go into our end. And once you've finished, it doesn't actually take you any time to finish. So, if we go through with our start times, these ones here, with nothing happening first, they can all start at 0. So, C is going to have to wait for B. This one started at 0. It's going to take 2 hours. So, C can start at 2. E has got to wait for both C and D. So C starts at 2, takes 4 hours, so they'll finish at 6. D starts at 0, takes 3 hours, so we'll finish at 3. So we've got to wait for a 6 and a 3. So the slowest one of those two is going to be 6. F, we're just looking at a 3. Then coming into G, we've got 3 and 1, which is 4. 6 and 2, which is 8. So we need to wait for the slowest one. Slowest one is going to be 8. Wrong box. Slowest one is going to be 8. And I is going to come in at 4. G starts at 8, takes 1. So J and H are both going to be 9. Because 9 is bigger than 4 and 1, which was 5, and 0 and 2, which was 2. So, waiting for the slowest one. So we have 9 plus 1.5 and we have 9 plus 3. 9 plus 3 is 12 and 9 plus 1.5 is smaller. So when we are going backwards, you've got 12 take away 0. 12 take away 0 means that this one's going to be 12 and this one's going to be 12. When we go backwards, we use the earliest deadline. So we've got 12 take away 1.5. So that gives us 10.5. That also puts a 10.5 into I. Now G has 10.5 coming in as a deadline from J, but 12 take 3 is 9, and 9 is the earlier deadline, so it's the one we have to use. Reason we have to use it is if one person gives you a deadline of 9 and one person gives you a deadline of 10.5, if you hand the stuff in at 10.5, the guy who gave you the deadline of 9, you're an hour and a half late. If you give both of them it at your deadline of 9, yeah, you're early for this one, but handing in something early is never going to be a problem. So, coming across into E, you've got 9 take away 1 is 8. Then we have still 9 take away 1 is 8, or 10.5 take away 1. So we've got 2 going in, and again we have to use the earliest. So 8 take away 2 is 6, so we'll have a 6 going in here. 8 take away 1 is 7, so that one would be 7. That one comes in as 6, so this is going to have to be 6. 6 take away 4 is 2. So that covers us for construction activity network. Earliest start times, which are the red ones, latest finish times, which are the blue ones, and our critical path or our critical activities. Critical path is basically where the maths works. So you've got 0 plus 2 is 2, so this is going to be critical. 2 plus 4 is 6, this one's going to be critical. 0 plus 2, not 10.5, 0 plus 3, not 6. 6 and 2 is 8. 8 and 1 is 9. So then we've got to figure out whether we go this way or this way. 9 plus 3 is 12. 9 plus 1.5, not 12. So our list of critical activities or our critical path is going to be B, C, E, G, H, and it takes a length of 12 hours. If we do the Gantt chart in a second, but the float at A, float is your distance or your time between what you need and what you've got. So in this case, you can start at 0, it'll take 2 hours, but you've got until 10.5. So what we're going to end up with is 10.5, take away the 2, take away 0, and that should give us 8.5 as our float for A. So that's 1F sorted. Our Gantt chart we are going to have to do on graph paper. I've not included graph paper because it photocopies really badly. So it will normally have some numbers along the bottom, doesn't normally have anything up the side. So if we start off at A, we start at 0. Now our duration is 2, so we've got a line that will go along that is 2. And then our final end time is 10.5, which is here. So we've got this massive bit of float. And that float is the same thing that we just worked out, which will be your 8.5. So for B, we're starting at 0, going up to 2. And we've got a duration of 2. So we don't have any float at all, which is what we'd expect because it's critical. C starts at 2, it goes along 4, and it finishes at 6. So again, no float because it's critical. D starts at 0, we have a duration of 3, so it's 3 boxes along. However, we don't stop until 6. So we have this first section, which is the duration, and we have the second section, which is our dotty float. E starts at 6, goes along 2, finishes at 8. So again, no float. F starts at 3, goes along 1, but finishes at 8. So this is the thing again with quite a lot of float. So doesn't have to be done at that specific first point, could be done at any time in this section. G.
I think it looks useful. It's very precise.
G starts at 8. It is 1 square long and finishes at 9. No float. H starts at 9, takes 3, finishes at 12. So again, no float, which is kind of what you'd expect given that it's on the critical path. I started at 4, took 1, and finishes at 10.5, which is up here. So we have solid block, and then our float, so the dotty bit up to 10.5, and then we've got J. J starts at 9, takes 1.5, and finishes at 12. So we've got solid bit 1.5, dotty bit up to 12 for our float. And that is our Gantt chart, which is 1E. Section B. So first off, we are asked to show the shortest direct walking time between the places here, and we can use the information here. So starting off at GA, we could go to LB, and that is 10. GA can go to BA, and that is 14. Or GA could go to MF, and that is 15. And those are our direct routes. They are the only direct routes for GA. Looking next to LB, because we've already done ones that are before, we don't have to worry about the top half of the table. So LB going to BA is 8. LB going to MF is 9. LB going to SP is 9. And going to MN is 6. Although it's not very often that you see it where they're asking you to actually complete the table, it is one of the things that is on the specification. So in theory, they can ask us. So BA to BP is 9. BA to PA is also 9. And then BA to SP is 7.
set using liquid nitrogen
and to MN
at minus 196
is
degrees
8.
Celsius. It freezes the mixture solid
So
in a matter of seconds.
MF to BP is 8. MF to SC we don't have on our map. MF to PA is 13. And that's it. BP to SC isn't on our map. To PA is 3. To SP that can go over the top there. That is 9. And BP to MN, if we take that round there, and that can squeeze up there, and that can come at 14. Then we didn't worry about that one. PA we've done. UG doesn't exist. SP is 8. We don't have PO on this map. We don't have PP. Don't have SS. But we do have SP to MN. And that is 7. So we've got our list all sorted. Prim's network starting at BP. So we are starting here. And we are looking for the shortest thing that is attached to BP. So that's going to take us down to PA. So we've got BP to PA, and that is 3. So if we highlight that, right, next smallest thing, we have 2 values of 8. It doesn't actually matter which one we choose. So if we go from BP up to MF, and that is 8. So we could have chosen the other 8. Didn't make any difference because there's nothing smaller than 8 there. What we've got now is we now know about MF, so we can go from there. So MF to BA is 1. So that's the smallest thing we've got. So the smallest thing out of here is going to be this 7.
Real challenge. It's a very unorthodox.
So we can go BA to SP is 7. Next smallest is this 7. So we've got SP to MN is also 7. Next smallest one is this 6. So MN to LB is 6. The next smallest thing we've got would be one of the 8s, but all of the other 8s are going to make a loop. So we'll take this 10 going up here. So we've got LB to GA is 10. So that sorts us out for 2B. So our minimum connector is PA to BP to MF to BA to SP to MN to LB to GA, and it has a length, and its length is 10, 20, 34, 42.
7 weeks ago, 64 determined
So we've got a length of 42.
set their sights on the MasterChef title.
Using the same minimum connector, which would have been the last if you had done Kruskal's. So Kruskal's goes smallest to biggest. So if we'd done Kruskal, we would have gone 1, 3, 6, 7, 7, 8, 10. So actually, this one is still going to be the last one, even if we'd done Kruskal's. So 2C, it would still be LB to GA is 10. Right, so Dijkstra. We are looking to find the shortest walking time between MF and PO. So MF and PO. We need to show all the temporary labels, so that's the bit where you cross it out neatly rather than scribble it out so they can still read it. So, if we're starting at MF, taking the amount of time to get to MF, it's where you already are, so it'll be no time. Box the smallest thing, 1 step in each direction. 1 up to 15, 1 down to 14, 1 down to 8, and 1 step across at 1. So then we box the smallest thing, in this case 1. So 1 and 14 still 15, 1 and 7 is 8, 1 and 9 is 10. We then box the smallest thing, which is 8. So if we box this 8, 8 and 7 is 15, which is bigger, so we'll keep the 14. 8 and 9 bigger than 8, 8 and 3 bigger than 10. So box the smallest thing, 8 and 10, we're looking at 18, 8 and 10, we're looking at 18, 8 and 6, we're looking at 14, 8 and 8, looking at 16. We then need to box the smallest thing. Ooh, and 8 and 9 is 17. Nearly missed one. So next smallest thing is this 10. So 10 and 7 is bigger, 10 and 8 is bigger. Next thing we've got to do is box the 14. Now we've got 2 options here. Sensible one to go for is this one, because this is our finish point, and so now we're done. Once we've got to our end point, we don't go anywhere else. So we can stop. We need to leave all the others unboxed. Not a problem if you've boxed the 14 as well, because 14 is the same as 14. So, our path is coming across 1 down to 8, and then 8 down to 14. So our path is MF goes to BA, goes to SP, goes to PO, and that has a length of this 14 here. Question 4. By inspection. This basically just means look at it. So the shortest time from MF to SP, we can either do this from our grid or from our network that we've just done. So to go from MF to SP is 8, and to go from MF to MN, we'd have to add in the 6 and the 7. So the shortest way to get there would be 15.
So I tried to keep it really true to myself and true to what I like to cook.
So, nearest neighbour algorithm. We are starting at MF, and nearest neighbour is a case of start where you're told to. then go to wherever is closest. So got MF, closest is 1 away, and that is BA. So BA, closest thing that we've not already been to is this 7, which is SP. So looking at the shortest one is going to be the other 7, going to MN. Then once we're at MN, the closest thing is 6 to LB. We've now been to LB, so the only place we've got left to go to is GA. So GA at 10. So we've now been everywhere, and now, because we've got neighbours, we've got to go home. So GA to MF is 15. So this gives us an upper bound, and our upper bound is going to be 14, 15, 30, 46. So we've got an upper bound of 46. If we used this tool, what would it be like starting at SP? So all we're doing is starting here instead. So it's going to be SP, MN, LB, GA, MF. So we've run out of space here, but we're already at MF, so we'll go BA. And then, because it's a tour, we've got to go home. So it'll be exactly the same length. It's just starting at a different place. So, table 2, this one, we have deleted MF. That's now gone. So, Prim's algorithm to find a minimum spanning tree. Minimum spanning tree first off. If they don't tell you where to start, it's fine. You may as well start on the first column. So, if this is our first place, we look down, find the we cross the first row out, we highlight the first column, and we choose the smallest one and add it to our list. So GA to LB is 10. So LB, second place we've chosen, cross it out, highlight it, so we can now choose anything from these two highlighted and numbered columns. Smallest thing that's there is this 6. So that is LB to MN is 6. So we cross out MN. MN is the third place we've gone. So now we can choose anything from this column, or this one. The smallest one we've got is this 7. And that is MN going to SP at 7. So we can cross it out, we number it, and we can now use it as well. So any of these four are available. Smallest one is SP to BA, also 7. So that is going to be the 5th one, so we can cross that out for completeness. We've got a total that comes in at 14, 20, 30. So, prims on tables. If we think about joining them up to make a tree, we've got GA goes to LB, goes to N, goes to SP, goes to BA. Not very exciting tree, kind of a line. So, we've got a minimum spanning tree, it's got a length of 30, beautiful tree. Hence. Hence in exam speak basically means use what you've just done. So, finding a lower bound, deleting MF. That's 4CII. So we need to choose the smallest 2 from MF. So that is MF goes 1 to BA and MF goes 8 to SP. So those are the 2 smallest. So if we add those together, we've got 1 add 8 is 9. Then we can add that onto our minimum spanning tree. So we've got 30 plus 9 is 39. And that is our lower bound. So part D, this is nice and easy. We've got use your answers. So we're going to have an upper bound, we've got a lower bound. And so we've got our lower bound is 39, our upper bound is 46, and T is in the middle. So we're going to need our inequalities pointing in the small direction. If we'd got more than one upper bound, we choose the smallest. If we'd got more than one lower bound, we choose the biggest. Basically, we're trying to squash T as much as possible.